Hello my friends and welcome back to the Today Machine channel. The construction of the Obervermentwerk 2 has been marked by a series of significant milestones in its development. A major achievement occurred early on when the final rock masses were blasted out of the powerhouse cavern, completing the excavation of the cavern to its maximum size. At the same time, concrete work began in the transformer cavern to prepare the foundations that would support the heavy transformers, weighing up to 200 tons. Concrete pouring also started inside the powerhouse cavern, even while blasting continued in other areas. Outside, work continued without pause. For instance, preparations for the outflow structure at Vermont were carried out during low water periods, ensuring everything was ready for the installation of the sluice gate, a steel mechanism designed to control the water flow. The sluice gate, which had to be delivered just before the road became impassable, was carefully installed with high precision to ensure it would withstand water pressures of up to 2,800 tons. Once the sluice gate was installed, further work on the outflow structure continued to ensure that the system was ready for the refilling of the Vermont reservoir. This structure had to be completed before the final segment of the underwater tunnel connecting the powerhouse cavern to the lake could be blasted. The successful breakthrough of the underwater tunnel marked another important step forward in the project. Following the breakthrough, efforts turned to testing the sluice gate's integrity. As the Vermont reservoir began to fill, the outer part of the outflow structure was gradually flooded. This allowed for detailed inspections of the sluice gate, the surrounding structure, and the surrounding rock to see how they responded to the increasing water pressure. At the same time, various companies were working on the steel, water, and mechanical components that would be used in the power plant. For example, at Kremmuller in Wels, Austria, metal sheets were bent and welded to form the large pump spirals, each with a diameter of 9 meters and a weight of 100 tons. These pump spirals are critical in moving water from the Vermont back into the Silveretta Reservoir. The metal fabrication was both time-consuming and labor-intensive, with specialists regularly visiting the factory to ensure the final product met the project's strict specifications. Once the pump spirals were assembled, they were carefully lifted and precisely machined with a special milling machine to ensure flawless manufacturing. These components are vital to the plant's function and will eventually be encased in concrete for long-term, friction-free operation. Another major development in the construction was the completion of the Silveretta Tunnel, which connects the Vermont and Silveretta Reservoir. This tunnel was particularly challenging due to water inflows, but the final excavation work was completed successfully, linking the new tunnel with the water intake structure in the Silveretta Reservoir. The completion of this tunneling work was celebrated as a significant achievement in the project. Additionally, important components for the Obervermentwerk 2 were being fabricated at other locations. In Wels, Austria, at Bilfinger, steel plates up to 37 millimeters thick were rolled, bent, and welded to form large pipes with a diameter of 4.5 meters. These pipes were then transported to the assembly hall below the Vermont Dam, where they were joined into pipe sections 10.5 meters long. Once the pipe sections were transported to the top of the steep pressure shaft, each weighed around 45 tons and had to be securely fastened. The next process began with the delivery of large structural components, which were initially transported via specially laid tracks to the upper water tunnels, where they were stored temporarily. This storage took place while excavation work continued in the machine cavern below. The parts were later welded together, inspected, filled with water, and backfilled with concrete to form a robust base for the machines that would eventually be installed. One of the most spectacular aspects of the project was the construction of the water shaft, located halfway between Vermond and Silveretta Lakes. This vertical shaft, nearly 300 meters high and with a diameter of up to 18 meters, played a critical role in pressure regulation. It was essential for managing transitions between turbine and pump operations. The shaft was constructed using a combination of drilling a pilot shaft followed by tunneling to full diameter from top to bottom, utilizing precise blasting techniques that required significant logistical coordination. The blasting also created a notable physical effect, with clouds of mist forming due to the rapid saturation of air moisture. These clouds quickly dissipated as they were drawn down by the debris. Following the explosions, the construction team began pouring the foundations for the massive machines that would operate in the cavern. These foundations required large amounts of reinforced concrete, which was carefully planned to accommodate pipes for cooling and wastewater, as well as electrical lines and other essential cables. With about 750 individual concrete pouring sections across the cavern, each was meticulously crafted to ensure there was sufficient space for all required infrastructure, taking into account the need for clean and dry conditions for the welding of stainless steel pipes. The concrete itself, around 25,000 cubic meters, was produced in a dedicated batching plant located near Vermond Lake. As the interior construction progressed, the focus shifted to the arrival and installation of large mechanical components, such as turbines and pump spirals. These components were transported by specialized vehicles through narrow mountain roads to the power station entrance near Vermond Lake. To fit the components onto the roads, parts of the spirals had to be detached, and even with the road closures in place, the transportation required careful maneuvering. In some cases, vehicles had to reverse for nearly a kilometer to reach the cavern. Once the turbine parts reached the cavern, they were reassembled, and each part was thoroughly inspected to ensure its integrity under the expected operational pressures. In the cavern, a 35-meter-high space was prepared for the subsequent installation of cranes that would handle the heavy components. Massive crane tracks were constructed, requiring careful planning of reinforcement and formwork. Once the crane tracks were complete, the crane itself, capable of lifting up to 180 tons, was assembled and positioned using a large mobile crane. As the machine components began to arrive, they were carefully placed in the correct positions. The spiral components, each weighing around 100 tons, were aligned with high precision, utilizing advanced measurement technology to ensure exact placement. Once in position, the components were encased in steel reinforcements and secured with 500 cubic meters of concrete. Additionally, the construction of tunnels for water inflow and outflow was critical. These tunnels needed to accommodate both the water system and the electrical cables that would transport the power generated by the turbines. A cable tunnel was built to connect the transformer cavern with the outside world, and the existing infrastructure, such as the Trenier Tunnel built in the 1920s, was expanded to facilitate the installation of new pipelines and asphalt roads for seasonal access. Safety features were also a key part of the underground construction. The cable tunnel was divided into two sections, one for cables and the other as an emergency escape route. As the project neared completion, the last remaining components, including the protective enclosures for the turbine shafts, were lowered into place. Key areas of focus include maintaining high-pressure resistance, ensuring watertight walls, and implementing secure welding procedures for all joints and seams. Rigorous testing is carried out following the completion of individual components to verify their integrity before moving to the next stage of construction. One of the significant tasks involves the finalization of an underwater tunnel, linking the machine cavern with the outflow structure in the nearby reservoir. This part of the construction begins with the concreting of the tunnel floor, followed by the installation of a circular lining on top of the concrete slab. Using a specially designed formwork vehicle, the entire 400-meter-long tunnel is then lined with concrete from bottom to top. The project team ensures continuous and smooth progress until the injection work, which will complete this section of the tunnel. At the outflow structure, work continued once the reservoir was lowered in the fall, making the construction site accessible again. This phase involved concrete pouring and, most notably, the installation of the intake screen. The most challenging aspect of this stage occurred in the water castle, a vertical shaft with a diameter of 6.3 meters. Concrete was delivered via cable from a remote location, and workers had to manage the logistics of lowering fresh concrete from heights of up to 300 meters. The concrete placement was achieved using a system that worked 24/7, with a specialized formwork traveling up the shaft as the concrete was poured, filling the structure steadily over several weeks. Meanwhile, preparations for energy transport systems continued along the steep slope leading to the Vermundbahn cable car. Due to the harsh conditions in this section, large concrete troughs for the 220 kV power lines could only be installed in summer. However, the majority of these troughs had already been laid, with the remaining sections completed later. High-voltage cables were delivered to the site, with heavy-duty transports bringing the first cable drums, each carrying up to 1,000 meters of cable, to be drawn into previously installed pipes. Additionally, in the Silveretta Tunnel, over 3 kilometers of tunnel work continued. The floor was first smoothed and then a concrete base layer was added. Prefabricated tunnel segments were positioned to allow a formwork vehicle to move along the length of the tunnel. The concrete lining was poured incrementally, with about 180 cubic meters of concrete being used every 14 meters of tunnel length. In the transformer cavern, significant work was carried out to prepare for the installation of 2 large transformers and other electrical components. The production of housing for 4 large ball valves, which serve as critical components to regulate water flow to the turbines and pumps, was handled by specialized manufacturers. These ball valves, built to withstand extreme pressures, required a thorough inspection before they could be delivered to the construction site. Precision components for the valves were produced by various specialized companies, including parts like the closing weights for the valves, which were meticulously crafted for exacting standards. The entire construction project relies heavily on coordination and collaboration between multiple teams, including civil engineers, steel construction workers, and machine builders. As the construction progresses, thousands of cubic meters of concrete are poured, tunnels and shafts are lined and reinforced, and heavy machinery is installed in various parts of the facility. Despite the challenges posed by the mountainous terrain and underground conditions, the project continues on schedule, thanks to precise planning and a dedicated workforce. The efforts of the skilled workers on site and the seamless collaboration between the different construction teams have allowed the project to stay on track and make significant progress toward completion. The overall objective is to create a fully operational facility that meets the stringent requirements for safety, efficiency, and performance, ensuring it will function reliably for many years to come. The PVC pipes extrusion line begins with the BA125 twin-screw extruder, powered by a 110 kilowatts motor, which ensures efficient and uniform material melting and mixing. The process is supported by 2 dosing and loading units, one for virgin material and the other for regrind material. A temperature control cabinet with an industrial PC Siemens S7 oversees precise thermal regulation throughout the extrusion process. The extruded material is shaped through a high-precision extrusion head, accommodating pipes up to 500 millimeters in diameter. Downstream, the line includes a 2-stage calibration trough, 10 meters long, capable of handling pipes with a maximum diameter of 630 millimeters. This is followed by a 6-meter cooling trough, which solidifies the pipe under controlled conditions. Further along, the pipe passes through a marking unit for identification, then moves to a 4-caterpillar haul-off unit that ensures smooth and consistent pipe transportation. A planetary cutting unit equipped with universal clamps trims the pipes to the desired lengths. Finally, an inline belling unit creates solvent cement sockets or O-ring grooves for pipe connections. The system includes specialized dies, sizers, and belling tools for pipe diameters from 160 mm to 500 mm, enabling versatile production capabilities. The steel industrial pipes and profiles manufacturing industry is a cornerstone of global infrastructure, with applications in construction, energy, transportation, and manufacturing. In 2023, the global market for steel pipes was valued at approximately $134.4 billion, with a projected compound annual growth rate of 4.5% from 2024 to 2030. The steel profiles market, including beams, channels, and angles, also witnessed robust growth, driven by increasing investments in construction and industrial projects. Steel industrial pipes are essential in transporting fluids and gases, with industries like oil and gas, petrochemicals, and water supply relying heavily on their durability and resistance to corrosion. Common types include seamless, welded, and electric resistance welded pipes. For instance, seamless steel pipes dominate due to their superior strength, accounting for nearly 60% of the total market. Steel profiles play a critical role in building frameworks, bridges, and machinery. With global urbanization rising, the demand for structural steel profiles is projected to exceed 650 million metric tons annually by 2025. Key products include I-beams, H-beams, and T-profiles, which offer high load-bearing capacity and design versatility. The industry's innovations are focused on sustainability and efficiency, such as using recycled steel. Globally, steel pipes and profiles manufacturing consumes around 40% recycled steel, reducing environmental impact. Furthermore, advancements in automation, such as robotic welding and smart manufacturing, have significantly enhanced productivity and quality control. Leading manufacturers are concentrated in countries like China, India, and the United States, with China producing over 50% of the world's steel pipes and profiles. Emerging markets in Southeast Asia and Africa also offer lucrative growth opportunities due to infrastructure development and energy projects. The repair and maintenance of active gas pipelines must strictly adhere to national standards for the gas industry. Such operations, including the integration of new pipeline sections or other modifications, are conducted without interrupting the flow of the transported medium. This document outlines the procedures using equipment produced in the Russian Federation by the firm Stoptron. Key stages of the repair process. Preparation of pipeline ends. The ends of the newly constructed pipeline are cut and prepared for welding. Simultaneously, the insulation on the operational pipeline is cleaned in preparation for installing purging fittings and a split T. Welding purging fittings and split Ts. A purging fitting and a split T with internal and external plugs are welded onto the pipeline. The split T is chosen to reinforce the pipe at the connection point. Installation of flanged adapters and valves. A DN400 flanged adapter is mounted on the split T, followed by the installation of a DN400 valve. This configuration ensures safe and controlled operations during subsequent cutting under pressure. Preparation of drilling machines. Drilling machines, including a DN500 unit for the main pipeline and a DN32 unit for purging holes, are equipped with pilot drills and centering bits. These are mounted and tested for operational readiness. Cutting operations. Using the drilling machines, purging fittings are cut, and pressure is equalized in the DN500 drilling machine through high-pressure hoses. The machine is then pressure tested to ensure integrity before the main pipeline cutting begins. Cutting the main pipeline under pressure. Once pressure testing is complete, the drilling machine executes the cutting operation on the active pipeline. This process is meticulously monitored to avoid disruptions to the gas flow. Removal and installation of internal plugs. After cutting, the drilling machine is removed. Internal plugs are installed in the split T to secure the connection. The drilling machine and associated equipment are then disassembled. Final sealing and insulation. An external plug is welded onto the split T to seal the system fully. The entire assembly is then insulated to ensure long-term durability and protection against environmental factors. Project overview. The repair site in focus involves a high-pressure gas pipeline operating at 12.10 megapascals. The objective is to connect a newly constructed gas distribution point, GDP, with a throughput capacity of 45,000 cubic meters per hour while decommissioning an existing GDP with a capacity of 24,000 cubic meters per hour. The task includes joining a new DN400, 26 mm pipeline to the operational DN400, 26 mm pipeline under pressure. The production process of drive systems and components in steelmaking plants and rolling mills demands precision and reliability to meet the high standards of product quality and plant availability. Companies like SMS specialize in designing and manufacturing these critical systems, integrating metallurgical and rolling mill expertise with advanced gear design. The product range includes main drive gears, mill pinion gears, twin drive gear units, tilting drives for converters, and gear components for shears, edgars, sizing presses, and coilers. Advanced spindles, such as gear type and slipper type spindles, cater to high torque applications. The manufacturing begins with submerged arc welding for gear wheels, followed by stress relief annealing. The machined components are crafted using state-of-the-art equipment under strict supervision. Case hardening enhances durability, and precision grinding ensures optimal gear tooth profiles. Each gear undergoes ultrasonic testing and rigorous measurement checks for quality assurance. Gear housings are fabricated in-house, and entire units are pre-assembled to optimize contact patterns and clearances using computer-aided programs. Modern facilities, such as this gear-making workshop in Hilchenbach, integrate all major manufacturing steps, ensuring top-quality production and shorter delivery times. Innovations include modular assembly for complex installations, exemplified by the rapid replacement of drivetrain systems in operational plants. The process is supported by advanced tools like 3D CAD systems, specialized calculation programs, and work schedules. Comprehensive service plans, including monitoring systems and preventive maintenance, ensure long-term performance and reliability, reinforcing SMS's position as a leader in drive technology for steelmaking and rolling mills. Dry cutting bevel gears is an advanced manufacturing technique that eliminates the need for cutting fluids, reducing costs and improving environmental sustainability. This method is particularly efficient for producing bevel gears used in automotive, aerospace, and industrial machinery applications. Dry cutting utilizes high-speed cutting tools made of carbide or other advanced materials capable of withstanding high temperatures. Modern bevel gear cutting machines can achieve cutting speeds of up to 2,500 meters per minute and feed rates of 1.5 to 2 millimeters per revolution, significantly improving productivity. The precision of these machines ensures a surface finish of raw 1.6 micrometers, meeting or exceeding industry standards. Advanced cooling technologies, such as air blast or minimum quantity lubrication, are used to manage heat generated during cutting. This approach minimizes thermal distortion and tool wear, extending tool life by up to 30% compared to traditional wet cutting methods. Additionally, eliminating cutting fluids reduces operating costs by approximately 15 to 20%, depending on production volumes. Dry cutting machines are versatile, capable of producing gears with module sizes ranging from 1 mm to 10 mm and diameters up to 800 mm. This precision and scalability make dry cutting bevel gear technology an ideal solution for manufacturers seeking high efficiency, cost savings, and environmental responsibility. At Doosan Machine Tool System Shop in Changwon Namsan Factory, an advanced system solution has been developed to efficiently machine aluminum wheels. This comprehensive machining line handles the process from raw material to finished wheels, ensuring high productivity and precision. Key machine tools applied in the solution are the Puma VA 800 and the Minx 5400 series. Puma VAW 800 series, high productivity vertical turning center. The Puma VA 800 is engineered specifically for machining aluminum wheels for motor vehicles and motorcycles. Its design includes a large machining area capable of handling wheels up to 27.5 inches in size, with a maximum turning diameter of 720 millimeters and turning height of 340 millimeters. Equipped with two powerful 6-station turrets, this machine delivers excellent cutting capacity and reliability. Features like a structurally improved spindle, a robust carriage system, and twin-chip disposal enhance productivity while maintaining a compact footprint suitable for automation with gantry or robotic systems. Minx 5400 series, heavy-duty vertical machining center. The Minx 5402 is a versatile and powerful machining center designed for heavy-duty milling operations. With a maximum spindle speed of 286.5 R per minute and Y-axis travel up to 550 millimeters, it ensures stable precision for various workpiece sizes. Its rigid structure, fast tool changes, and user-friendly NC system simplify operations, boosting efficiency and reliability. This integrated system solution exemplifies Doosan Machine Tools' commitment to delivering high-performance, automated machining for aluminum wheel manufacturing. Creating a replacement brass knob for a gas fireplace involves several precise machining steps. This one-off piece required the use of pre-existing CNC code, prioritizing simplicity over speed or efficiency. Since it was a custom, single-piece project, there was no need to optimize the toolpaths further. Instead, the focus remained on achieving the correct shape and dimensions. The machining process started by securely mounting the brass stock onto the CNC machine. The toolpaths guided the cutting tools to shape the knob, carving it from the raw material with precision. Despite the slower and less efficient toolpaths, the process ensured the desired quality and accuracy for this unique replacement piece. Once the CNC machining was complete, additional manual operations were performed off-camera. The knob was cross-drilled and tapped to accommodate a set screw. This set screw plays a critical role in securing the knob to the shaft, ensuring a firm and functional attachment. Had this been a production run, optimizing the CNC code to minimize machining time would have been essential. However, for a single-piece project, utilizing the existing code saved programming time while still delivering a high-quality result. This approach highlights the flexibility and practicality of CNC machining for both custom and production applications. The Portal Milling Machine VM6545 is a robust and versatile machine designed for precision machining tasks. With a spacious working travel range of by 6,500 mm, Y 4,500 mm, and Z 1,500 mm, it is ideal for handling large and complex components. The machine is equipped with an advanced CNC control system, the Heidenhain TNC 640, featuring a color touchscreen for user-friendly operation and precise control over machining processes. A key feature of the VM6545 is its automatic milling head exchange system. The machine includes a fully enclosed and contamination-protected storage unit for up to 3 milling heads. Positioned at the rear of the work area, this storage system doubles as the rear wall of the machine. The process of opening and closing the storage, as well as lifting and depositing milling heads, is entirely automatic, ensuring seamless and efficient transitions between different machining operations. Additionally, the VM6545 boasts an automatic tool magazine capable of holding 50 tools with HSK 100 interfaces, further enhancing its flexibility. A chip conveyor with an increased ejection system ensures effective removal of machining debris, maintaining a clean work environment. This combination of advanced features makes the VM6545 a highly capable solution for demanding industrial applications. The bar springs industry is a critical segment of the global mechanical components market, valued at approximately $3.5 billion in 2024 and projected to grow at a CAGR of 4.2% from 2024 to 2030. Bar springs, known for their strength and durability, are widely used in automotive, aerospace, heavy machinery, and energy sectors. In the automotive industry, bar springs are vital for suspension systems, accounting for 35% of the total demand. With global automotive production exceeding 80 million vehicles annually, the market for bar springs in this sector alone is substantial. In the aerospace sector, bar springs are used in landing gears, with demand growing due to increasing aircraft production, which is expected to surpass 1,200 units per year by 2025. Material innovations, such as high-strength steel and advanced alloys, are driving performance improvements. For instance, high-carbon steel bar springs can endure up to 20% higher loads compared to traditional materials, making them suitable for heavy-duty applications. Manufacturing advancements, including CNC-controlled forming and heat treatment processes, have enhanced precision and longevity. These processes ensure bar springs achieve fatigue life cycles exceeding 1 million load repetitions, meeting stringent industry requirements. The Asia-Pacific region, led by China and India, dominates the market, contributing 45% of global production. Europe and North America follow, driven by demand from automotive and industrial equipment manufacturers. The industry faces challenges such as raw material cost volatility and stringent environmental regulations, but continuous innovation ensures its pivotal role in modern engineering solutions. It begins with 3D tool design and the milling of tools, followed by CNC high-speed cutting to create the necessary precision for crafting scissors. A blank piece is split and heated to 1040 degrees Celsius for forging, where the initial shape is formed. The contours are then carefully cut, and the finger rings are precision ground both inside and outside to ensure ergonomic comfort and accuracy. The blanks undergo heat treatment at temperatures exceeding 1000 degrees Celsius, followed by ice hardening at -180 degrees Celsius, enhancing their durability and resilience. Machine grinding refines the surface, while the pivot joint and handles are polished to perfection. Hand grinding ensures a fine finish, and polishing further enhances the aesthetics of the scissors. For specialized designs, thinning teeth are eroded using advanced techniques. Quality is paramount, with inspections carried out at various stages. Computer-aided fine-tuning ensures precise alignment and performance. During assembly, the inside cutting edge is honed, and the tip is polished for optimal sharpness. Each pair undergoes rigorous tests to inspect cutting action and functionality. Laser marking adds branding or customization, completing the manufacturing journey. The final product is visually inspected and packaged, ready for use. This dedication to craftsmanship ensures that every pair of scissors from Solingen is a masterpiece of precision, durability, and ergonomic design. The double-deck roofing sheet roll forming machine efficiently produces two different models of roofing sheets on a single machine, optimizing space and cost. The upper and lower layers are equipped with separate rollers to form distinct profiles, allowing seamless switching between sheet designs. Sheets are fed into the machine, where they are precisely shaped by roll-forming dies designed according to required sizes. The machine can be customized to meet specific dimensions and profiles. It is controlled via an automated system for accuracy, speed, and ease of operation, ensuring high quality and consistent sheet production for diverse roofing applications. The automatic folder gluer machine is a highly efficient and fully automated solution for producing corrugated carton boxes. It integrates feeding, gluing, folding, counting, and stacking functions, ensuring energy-saving and labor-saving operations with a gluing speed of up to 150 meters per minute. The machine is equipped with a digital control system, PLC programming, and double-frequency converters for precise and reliable operation. The feeding department employs an adsorption-type belt system for stable and accurate paper feeding. Its electromagnetic clutch and brake system allow for independent control, making operation straightforward. The creasing wheel is adjustable to handle cardboard thicknesses between 2 to 8 millimeters. Additionally, the motor speed is frequency controlled and synchronized with the glue folding department, achieving speeds up to 130 meters per minute. The front baffle and feeding unit belts can be adjusted quickly to accommodate various cardboard sizes and lengths. In the glue folding department, the main motor features frequency control, ensuring quiet and stable performance. High-quality stainless steel gluing wheels apply glue evenly, reducing waste. Imported wear-resistant conveyor belts fold cardboard accurately and automatically. The folding process is further refined with paper and creasing corrective devices and precision shaping wheels. The left and right baffles are electrically adjustable for easy operation. The foam industry in China has witnessed significant growth, driven by expanding applications in construction, automotive, packaging, furniture, and electronics. China's position as the world's largest manufacturing hub has further bolstered the demand for various foam materials, including polyurethane, PU, polystyrene, PS, polyethylene, PE, and polypropylene, PP, foams. Market overview. The Chinese foam market was valued at approximately $16.8 billion in 2023 and is projected to grow at a compound annual growth rate of 5.6% from 2023 to 2030. The rise is attributed to increased infrastructure development and automotive production. For instance, China's construction industry grew by 7.5% in 2022, fueling the demand for insulation foams like PU and expanded polystyrene, EPS. Key segments and applications. Construction. The construction sector accounts for nearly 35% of foam consumption, particularly EPS and PU foams for thermal insulation. The introduction of stricter energy efficiency standards has boosted the adoption of these materials. Automotive. Accounting for about 22% of foam usage, the automotive industry employs PU foams extensively for seating, headrests, and interior linings. In 2023, China produced over 27 million vehicles, creating substantial demand. Furniture and bedding. The furniture segment contributes 20%, with flexible PU foams being a primary material. China's furniture exports, valued at 87 billion United States dollars in 2022, underline the demand for quality foam materials. Electronics and packaging. Expanded PE and EP foams are widely used in protective packaging. The packaging industry in China, valued at 122 billion United States dollars in 2023, ensures steady demand. Challenges and opportunities. While facing challenges like stringent environmental regulations and fluctuating raw material costs, the foam industry in China has embraced eco-friendly and recyclable alternatives, such as bio-based PU and biodegradable EPS. China's growing domestic demand, robust export market, and innovations in foam production position it as a global leader in this sector.